Welcome, everyone. Today, we are diving into one of the most elegant and crucial systems in the human body, feedback mechanisms in endocrinology. If you have ever wondered how your body knows exactly when to produce a hormone and when to stop, you are in the right place. This concept is the absolute foundation of how our bodies maintain balance, adapt to stress, and survive. Let us get started. Now that we know what topic we are covering, let us build some intuition. Imagine you are driving a car on the highway and want to stay exactly at 60 miles per hour. If you see the speedometer drop, you press the gas pedal. If it creeps up, you ease off. This constant checking and adjusting is exactly how your body controls its internal environment, a beautiful process called homeostasis. In your body, the speedometer is a sensor in your brain, and the gas pedal is the release of hormones. When levels get too high, the body hits the brakes. Building on that car analogy, let us look at the formal definition. In endocrinology, a feedback mechanism is a physiological control loop where the output of a system regulates its own production. The most common type is negative feedback. This is where an increase in a target hormone actually inhibits the release of the upstream hormones that originally stimulated it. It is a self-limiting system. Occasionally, however, the body uses positive feedback. Instead of hitting the brakes, the hormone's release stimulates even more of its own release. This drives rapid, explosive physiological events like ovulation or childbirth. So, we understand the definitions, but why do these complex loops matter so much? Without them, our endocrine glands would just continuously pump out hormones until our blood became toxic, or they would fail to respond when we desperately needed them. These mechanisms are the absolute foundation of endocrine health. In real life, doctors use these feedback loops every single day to diagnose diseases. For instance, if a patient has high thyroid hormone but low stimulating hormone, the doctor knows the feedback loop is broken at the thyroid gland itself. Understanding this is the master key to endocrinology. Now that we understand why feedback matters clinically, let us look at its mathematical model. This differential equation balances how fast a hormone is secreted against how fast it is cleared from the body. The term dC over dt is the rate of change of the hormone. S max is the maximum secretion rate if there were no inhibition. C target is the feedback signal in the blood. K is the receptor sensitivity. If K increases, the gland is more easily inhibited. Finally, lowercase k is the clearance rate. The actual hormone level is a tug of war between secretion and clearance. With our formula established, let us apply it to a concrete example. Imagine a patient whose pituitary gland secretes thyroid-stimulating hormone. We are given a maximum secretion rate of 100, a feedback sensitivity of 4, a clearance constant of 2, and a target thyroid hormone concentration of 6. We need to find the steady state concentration. Because it is a steady state, the rate of change is exactly 0. We plug our given values into the formula, simplify the denominator, and solve for C. The final answer is 2 units, meaning the patient maintains a stable hormone level. Now that we have successfully found the answer, let us break down the mathematical reasoning step by step to truly understand how the biological brakes are applied. We start by setting the left side to 0, which mathematically states that the rate of secretion perfectly matches the rate of clearance. Next, we move the clearance term, 2 times C, to the left side of the equation. On the right side, we multiply the feedback sensitivity, 4, by the target hormone concentration, 6, to get 24. This multiplication shows exactly how strongly the target hormone is suppressing the secretion. Continuing our derivation, we simplify the denominator by adding 1 and 24 to get 25. This number is crucial. It is the suppression factor, representing the total resistance to hormone secretion caused by the feedback loop. We then divide the maximum rate of 100 by this suppression factor of 25, which gives us 4. This means that under these specific feedback conditions, the pituitary gland is only secreting 4 units per day. It is heavily suppressed from its theoretical maximum of 100, highlighting how effective negative feedback is at preventing overproduction. In this final step of our derivation, we take our simplified equation and divide both sides by the clearance constant, 2, to isolate the variable c. This gives us our final result of 2 units. Physically, this proves that the patient will maintain a steady TSH level of 2 units in their blood. If their thyroid gland were to fail and the target hormone dropped to 0, the suppression factor would disappear. The TSH levels would then skyrocket, which is exactly the mechanism doctors observe in a condition called hypothyroidism. This completes our understanding of the negative feedback model. Having thoroughly proven how negative feedback suppresses hormone levels, let us shift to positive feedback, which does the exact opposite. Instead of dividing and suppressing, positive feedback multiplies and amplifies. The formula is S equals S base times the quantity 1 plus P times E. Here, S is the new secretion rate. S base is the normal baseline rate. P is the positive feedback multiplier, representing sensitivity. And E is the concentration of the stimulating hormone, like estrogen. As the stimulating hormone E increases, the entire term in the parentheses grows, causing a massive spike in the final secretion rate. Let us see this amplification in action with an example from the menstrual cycle. We want to calculate the luteinizing hormone secretion rate right before ovulation. We are given a baseline secretion of 10, a positive feedback multiplier of 0.5, and an estrogen concentration of 8. We choose the positive feedback formula because estrogen stimulates luteinizing hormone. We substitute our values into the equation, multiply 0.5 by 8 to get 4, add 1 to get 5, and multiply by the baseline of 10. The final answer is 50 units per hour, a massive physiological spike. Now that we have calculated the surge, let us break down the math to understand the intuition behind this runaway effect. We start by looking inside the parentheses, which represents the amplification factor driven by rising estrogen. We multiply the positive feedback sensitivity, 0.5, by the estrogen concentration, 8, to get a stimulation factor of 4. This shows that the estrogen is providing a massive stimulatory signal on top of the baseline. The higher the estrogen climbs, the larger this stimulation factor will become, creating the explosive runaway effect characteristic of positive feedback loops. In the final steps of this derivation, we add the baseline factor of 1 to our stimulation factor of 4. This gives a total amplification factor of 5. The baseline factor of 1 is mathematically crucial. It ensures that even if there were 0 estrogen, the gland would still secrete at its normal rate. Multiplying the baseline rate of 10 by this amplification factor of 5 gives our final secretion rate of 50. This perfectly illustrates how positive feedback creates rapid, explosive physiological changes. Once the egg is released, the loop is broken, and the system returns to normal. To visually reinforce what we have just learned and proven, let us look at a diagram of the hypothalamic-pituitary-thyroid axis. At the top, you see the hypothalamus releasing TRH, which stimulates the anterior pituitary. The pituitary then releases TSH, stimulating the thyroid gland to produce T3 and T4 hormones. Notice the green arrows representing positive stimulation. But look at the red dashed line looping back up. This represents the negative feedback we calculated earlier. As thyroid hormone levels rise, they travel back to inhibit both the pituitary and hypothalamus, acting as the biological brakes. We have covered a lot of ground today, so let us summarize the most important ideas. First, feedback mechanisms are the biological thermostats of the human body, ensuring hormone levels remain perfectly balanced. Second, negative feedback is the most common type, acting as a braking system to maintain homeostasis and prevent toxicity. Third, positive feedback is rare, but absolutely essential for driving rapid, temporary events like ovulation. By understanding how these loops connect mathematically and biologically, you can predict how the body will respond to stress or disease. You have mastered the first major step toward thinking like a true endocrinologist.